Welcome guys to Unit 1 in Chemistry. Let's turn the lights off so it looks a little bit prettier. Unit 1 in Chemistry, this is just an introduction to chemistry. Introduction to chemistry, why are we here, what are we doing? First thing we're going to talk about is safety. We're not going to, and I realize we're not going to have normal labs this year, but when you are in the lab, when we do things in the class, you do need to know some important safety things. And when we do come back face to face, you're going to need to know this important safety stuff. The number one rule of safety in any science class that you'll always do is going to be just straight up use your common sense. If something doesn't seem like you should be doing it, don't do it. If you want to try something and you're not sure about it, ask me. I'll probably say, sure, mix those together. But there is that one time where I might say, no, don't do that. It's going to cause a bad gas to fill the room, or it's going to cause an explosion. Don't do that, and just use your common sense. If you're using glassware and you put it above a heater, Bunsen burner for 20 minutes, you're not going to pick it up with your hand. Common sense. Use your common sense. You should be fine. Other things, we try to avoid horseplay. If you have glass and things, pushing people around, especially if it gets crowded, you can knock things over. No unauthorized experiments. Most of the time, I'll let you do pretty much anything you want to do, but there are the ask first. And if there's something that we shouldn't do, I'll tell you not to do it. And of course, the most common thing that happens in a science lab that causes a problem is broken glassware. People don't realize that every surface in here just about is going to be easy to break glass, and just be careful when you're dealing with glass. Okay, rolling on. Some safety features we have here in this lab. Mr. Butterworth's class, we actually have the safety shower. Safety shower, you pull a string, water douses you. Any guesses on when you might want to use that?
I guess your eyes are on you.
Eyes, maybe, but that would be more this right here, the eye wash. What'd you say?
Catch on fire.
It actually is not for catching on fire, because sometimes if you catch on, no, that's a good thought. But sometimes when you catch on fire, the water could actually make it worse and make the fire spread around. The safety shower is for you when you get chemicals all over your body. If you got a chemical, like maybe you were holding something and you dropped a container and it just like splattered all over you, and you need to get those chemicals off fast, safety shower. We've never had to use it in the history of Aiken-Grifton. I don't plan on using it now. If a person catches on fire, you use a fire blanket. Smother that fire, cut it out, stop, drop, and roll, get the fire blanket, cover that fire up, okay?
Who can use a fire blanket?
What do you say?
Okay, so say if I catch on fire, you'll get a fire blanket.
But when anytime we're using, we have a portable one. Mr. Butterworth has one on the wall, but we have a portable one that anytime we're using fire in the class, we'll have it on one of these front desks. So if we do need it, we can use it really quick, okay? Fire extinguishers in the back of the room. That's if something other than a person catches on fire. It doesn't really work very well with a person because you can get all the junk from the fire extinguisher on them. But hey, if there's a fire, there's the fire extinguisher. You point, you click, you rock and roll. Eye wash is right here. If you get chemicals in your eyes, you hold yourself over the eye wash for about 15 or 20 minutes. Make sure you get all those chemicals out. Fume hood we don't really use much anymore, but we do have one over in Mr. Butterworth's room. It's for when you're doing chemical experiments that are going to be making things you don't want to breathe. And so our fume hood is actually disconnected because we don't do any of those experiments, but we could if we needed to. Material safety data sheet. Every single one of our chemicals that we use in this class has one of these papers digitally on our computers, and it tells us everything we need to know about the do's and don'ts, things we see on those chemicals. Couple words that people misunderstood when it comes to chemical exposures: acute and chronic. Acute is going to be a one-time exposure. Bam, you get hit with something, that's an acute exposure. Chronic exposure is exposure over long periods of time. So for example, if you have an allergic reaction to something, that's an acute exposure. You eat a peanut and your throat closes up, that's an acute exposure. You ever seen the commercials, mesothelioma? If you or a loved one has mesothelioma, call this number, blah, 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 blah. Y'all don't watch TV anymore, so you've probably never heard of it. But if you do watch the afternoon TVs, those come on a lot, that will be chronic exposure. That will be exposure over a long period of time. smoking cigarettes, breathing in chemicals. Those will all be chronic exposure over a long period of time. It doesn't necessarily mean good or bad. A lot of people think acute is bad, or acute is good, chronic is bad, things like that. It doesn't mean a little bit or a lot. It's all about time. Short exposure is acute, long exposure is chronic. LD50 is just a way that you can test how dangerous a drug is. The lower the higher the substance, the lower the substance LD50, the less it takes to kill you. It's a good way to understand things. So if you look at this, chemical A has LD50 at 3.2 milligrams per kilogram. Chemical B, 48 milligrams per kilogram. Chemical A is much more dangerous. Chemical A is more dangerous because it takes less to hurt you, okay? So that's the safety stuff. Let's just talk a little bit about the science and why it matters. So what do we do science for? What are the functions of science? These are two words that kind of get tossed out a lot when you first start learning about what science is: pure science and applied science. Pure science is what we're going to do in this class. Pure science is learning things, search for knowledge, facts. Oxygen is number 8 up there on the periodic table. It's O. It has a mass of 16. It has an atomic number of 8. That's all pure science, okay? Applied science is where you take that knowledge and you do something with it. Since I know oxygen has a mass of 16, then I know it will combine with hydrogen in this way to make water, blah, 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 blah. That's applied science, doing it, building something. So for example there, I used oxygen. This example is aluminum. Aluminum is strong, lightweight, good conductor. That's the pure science. The applied science is, since it's strong and light, I'm gonna make airplanes out of it. I'm gonna make baseball bats out of it. Since it's a good conductor, I can make pots and pans out of it. All about cause and effect relationships. If this happens, then this happens is another thing that science helps us with. Risk-benefit analysis. Should we do something or should we not do something? Making decisions in the world, science can help us with. We're seeing a lot of this with COVID. You know, the risk-benefit analysis. You know, it's a risk for us to come to school, but we get the benefit of actually getting the school thing. So we have to go, you know, is it worth it to do this? And that's where you really have to consult the science and look at the data and talk to people who are studying this type of thing. So next thing we got here is scientific knowledge. I love this picture because this picture, to me, embodies what science is. Who's doing science in that picture? You could make an argument for both. What kind of science do you think that dog is doing? What do you think that dog is thinking? What do you think that dog is thinking in this picture? What is this thing? Can I eat it? You know, can I run? Do I need to run from it? Is it scary? The frog's probably thinking, oh my goodness, what is this big giant thing? Will it eat me?
Oh, I can't see the frog.
Okay, oh, I'm sorry, I already got the block back there. But this is kind of the big steps. You know, we're gonna talk about scientific method in a second. To me, this is kind of a summary of the scientific method. It's gonna begin with curiosity. What is that? What's going on? What is this? Then you get this first real big important step in science, good observation. What's an observation?
Something you take, like, something that you take is something that you don't know, like you don't know what it is, but you take it like an observation of it. Maybe like kind of like a hypothesis, kind of.
Getting to a hypothesis a little bit. Observation is taking in information. I think that's what you're trying to get at. Okay, taking information, using your 5 senses. What does it look like? What does it smell like? What does it taste like? What does it feel like? Observation is getting information about something that you don't know about. Okay, most of the time we think about observation as just looking. But it can be lots of things. What does it sound like? Those are all good observations. Then once you make those good observations, you need to make a determination. Okay, so we have the dog here. Maybe the dog made an observation that this thing is little and looks juicy, what might be a determination from this thing is small and looks juicy?
Maybe you eat it.
Maybe I can eat it. That's a good determination. Maybe I can eat it. That once you take your good observations, now we can make a determination. Maybe I can do this. Now, flip side of that, the frog is looking up at the dog and saying, this thing is big, it's got some big old teeth, it's sniffing me, it might try to eat me. The determination is maybe I need to what? Maybe I need to get away. Now, a lot of folks stop there with science. They take their observation and they make a determination and they're done. I've looked at this, I've seen the data, I made a determination, I'm done, this is the way I feel about the data. But good science has to go on this next step. Good science has to include persistence. I know what it means to be persistent.
Constant.
Yeah. You don't what? You don't stop. Very good. You never stop observing. You never stop rethinking your determination. Okay? You never stop continuing to second guess yourself. You know, another thing, word in science is we call this being cynical. Always questioning, always thinking, you know, is this the best answer? Because if you stop here and you make a determination and you're done, that's crappy science. Because you might get new information. Okay? So the frog said, okay, this thing's going to try to eat me. It makes a determination, it needs to probably hop away. Well, if it made one hop and stopped, what would it do?
Still be eaten.
Yeah, because it wasn't persistent. Okay? So let's roll on. You got to give it a kick. Be a man. You can do it. I believe in you. There you go. You the
I'm
man.
trying to get him, but he's got headphones on. I can't.
I hear you. You got your master key?
Yeah, dude,
Yeah.
large in on.
No, he's not nervous.
Yeah, he's in there.
Oh, okay.
Watch the movie, but whatever.
He'll be fine. You're not gonna bother him. Sorry, video. All right. So look at the scientific method. How about what's my timer like, guys? 12 minutes, guys. All right. Let's roll on with the scientific method. Okay. We already kind of mentioned this. The key is to be a good observer. Be able to really, really look at something. Don't see what you want to see. See what's there. A lot of times with crappy science, folks say, okay, I'm going to go and look at this, and they know exactly what they're looking for. If you know exactly what you're looking for, you're probably going to see it. Good observers show up with nothing and just see and hear and smell and taste. And they take in things without anything that comes before. So let's look at the difference between these two words. Observation, we already mentioned, using the 5 senses. Inference is taking the next step, okay? So for example, an observation might be that when I see a new student, I see them and they are really tall and they got long arms and legs. That is an observation. What might be an inference I can make? If a new student is really tall and has long arms and legs, well, I don't have my coaching shirt on. Y'all know what I coach. You know what I coach. What do I coach? I coach tennis. If I see a student coming in that's really tall and with long arms and legs, I'm going to make an inference that, hey, maybe you'd be good at tennis or basketball or some other sport. Okay? Now, am I seeing them play tennis? No. Am I seeing them play basketball? Of course not. But because I've seen people that were tall and had long arms and legs before that were good at tennis, I can make that inference that because you have long arms and legs, you're going to be a good tennis player. So that's an inference where you're taking that next step, where you're making another judgment or an assumption. A lot of people downplay this. Don't assume. Y'all heard that before, right? I'm sure. Don't assume, you know. But, you know, making assumptions is part of who we are. And it's part of understanding that's what it's going to be. Even though I've never seen a certain chemical act a certain way, if I've seen another one that's similar, I can make an assumption about it. And that's okay. So don't just discount those types of things. When I get observations, I call that data. two different types of data, qualitative data and quantitative data. And you can look at the root words there, quality and quantity. Qualitative data is going to tell you about something when it comes to its quality, a description, okay? So if I want to describe my gnome here, my ECU garden gnome, what's the description I could say about this? What's some qualitative data you can give about my garden gnome? It's got purple clothes on, perfect. Another one? It's wearing a hat.
It's got a beard.
It's got a beard, black shoes, qualitative data. It's relatively short. That's still qualitative data. Now, to be quantitative data, what would I have to add to those things? I wouldn't just be able to say it's short, I would have to say what? I would probably have to break out a utensil to see how short.
See how short it is.
What would I have to tell you?
Its height.
How would I do that? Well, what do you need to tell something's height or what?
Something to measure it with.
Yeah, but once I measure it, what am I going to tell you? I'm not just going to measure it and say, nope, it's short. I'm going to measure it and I'm going to say, how? He said the exact height. I'm going to say a number. It's 13 inches tall. Okay? Quantitative data, you got to have numbers. So qualitative data does not have numbers. Quantitative data has numbers, your measurements. So clear liquids, qualitative, 55L. Anybody know what that is? Very good. 83 degrees Celsius, absolutely. Okay, so qualitative data tells me about it. Quantitative data gives me a measurement, gives me a unit. So the first thing, I'm gonna add steps to these as I go, but let me try to write no more. Oh, what happens if I try to write no? Let's see. There we go, that'll work. First step in scientific method, what do you want to do? Identify your unknown. What do I want to know? I always like using a silly example, so let's use my silly example today. My unknown is I want to know if people can fly. Everybody good with that? Okay, so I've identified my unknown. Can people fly? Second step is to make a hypothesis. Now, one of the most important things about making a hypothesis is the statement that you make it, how you make it. It must be testable, and usually a good hypothesis uses the words if and then. So you're testing one thing to see if one other thing will happen. So I want to see if a person can fly. My hypothesis, if you jump off the roof, then you will fly. Now, that's a silly hypothesis because you guys got good sense, and I'm breaking the number one safety rule, right? Usually common sense. But it's a way to think about it. Is it testable? Yeah, because what can we do? Jump off the roof. So it's testable, it's a prediction. If you jump off the roof, then you will fly. Now, a crappy hypothesis would be, if you jump off the moon, then you will fly. Why is that a crappy hypothesis? Because we're not going to the moon. Now, it might be a good hypothesis for the folks at NASA, but for us, it'd be a crappy hypothesis. Okay? And then next up, once you get that, you're going to repeatedly experiment. You're going to repeatedly experiment to test the hypothesis. Now, the experiment, you have a procedure and you have variables, but the big thing about the experiment is you have to be controlled, a controlled experiment. You have two groups. You have two groups for the experiment, a control group and an experimental group. And I think that's on the next page. Yep. You have two setups that differ by only one variable. So let's go back to my hypothesis. If you jump off the roof, then you will fly. So I need two people on the roof. About the same size, about the same weight, about the same age, everything about the same, except for I'm going to tell one person to jump and the other person stay still. So that's a controlled experiment. Now I need both of those because if I only have somebody jump and they start flying, well, I don't know whether or not it was jumping that made them fly. Because maybe a gust of wind came up and just picked them up. And I would be able to tell because the person standing beside them would also take off and fly. Make sense? Okay? Now, I can only change one variable. So a good hypothesis will be that setup. One person jumps, one person doesn't. Here's a bad one. If you jump off the roof and flap your arms, then you will fly. What might be a problem with that? So I have one person jump off the roof and flap their arm, the other person stays still on the roof. If the person flew, why did they fly?
They fly their arms.
Maybe. Or maybe it's because they jumped. You tried two different things. This is why when you test a medicine, you give one group a placebo, a sugar pill, and you give the other group the medicine. You don't just give one group the medicine and one group nothing, because then you're testing two things, whether or not you got the medicine and whether or not you took a pill. So you always change only one thing. And then finally, your conclusion must be based on your data. So many people are doing science, like I said, looking for something. And if you're looking for something, odds are you're going to find it. If I give you a whole bunch of money and say, hey, go do some research to prove that this gnome is safe to use in classrooms, you're probably going to come back to me and say, hey, guess what I found? It's safe to use. But what if your conclusion is not based on any data? What if your conclusion is just saying? You have to be able to back your conclusion up with real data. Okay? We see this all the time on Facebook, on Twitter, on TikTok. People just saying things without any data to back it up. Science doesn't care about what you think. Science doesn't care about how you feel. Science doesn't care about what you believe. Science needs data. Science needs numbers. How are we looking on time?
About done right now.
It's 22 minutes.
22 minutes. All right, let's stop there and we'll talk about law versus theory tomorrow. Thank you guys for paying close attention.